Now let's talk about the details of a journal bearing, which basically is a set of journal, which is our shaft, and the bearing. So this diagram basically shows all the details that we need to know. All right, first of all, the original location of the journal, which is concentric to the bearing. Due to load application and relative motion, this journal is displaced. So the center is at a displaced location. We connected two centers together, this line over here. Okay, so this becomes our new coordinate. Our all the calculation or analysis start from here, from this theta angle. All right, we have on the other side here, we define the minimum film thickness. So before the minimum film thickness, we have the convergent wedge. And after that, we have divergent wedge. So pressure is built up at this convergent wedge. You see this profile shows the pressure. All right, so it starts from 0 to at this side and gradually increase, and then reaches maximum before the minimum film thickness location, and then drops into 0. All right, so I showed here all that the pressure is toward the center of the shaft. And integration of the pressure would give us the force that balance the applied load I show over here, the vertical load. Okay, but between this load and the center line, there is an angle. And also I show here clearance, and I show any location, at any location this film thickness, which is this red line, H. All right, so now we have to talk about all of these. Now we need to define the mathematical terms for the journal bearing. Okay, so nominal diameter, we use the bearing diameter. So I use bigger D, and R is for the radius. Okay, correspondingly, we have the shaft diameter. I use small d and small r. However, as I mentioned several times, the difference between the two diameters, the bearing diameters and the shaft diameters, is very small. Okay, basically it is only the tolerance. So the tolerance determines the difference between the two diameters. Okay, and also in this direction, which is the axial direction, we define bearing width, or sometimes people call bearing length, which is L. And then, as I mentioned, radial clearance is between the two radius. Okay, I expressed them over here, but we know this is only due to the tolerance. Okay, now let's see the other things. Minimum film thickness, mentioned to you over here, I point out over here already. We see this in a previous movie too. Okay, and then we have the eccentricity, which is, I'm showing over here, along this center line. So basically it's a center displacement. All right, so the eccentricity shows the maximum shaft center displacement. Okay, that is the tolerance, the clearance, okay, clearance C, which is also over here, okay, over here, okay, clearance C minus the minimum film thickness. Non-dimensionalize this one by clearance, we get eccentricity ratio, okay, and we use eccentricity ratio to express the film thickness, which becomes this equation. These three things are from the previous movie. This is a short review. Okay, load, as what I mentioned over here, it is W, okay, vertically applied. There's an angle between load and the center line, okay, and this angle is defined as phi, which is the load angle, or sometimes people call position angle, or the attitude angle. They're basically the same thing. We can also define the average pressure. So that is load divided by the cross-section area. What is the cross-section area? Okay, so here, diameter and bearing length. So that is the cross-section area. So we can define the average pressure. Okay, another very important thing is sum of the number. Summerfield, basically this number is due to the mathematician who provided the first analytical solution to general baryons. That is when the baryon is infinitely long. So the solution, the Summerfield solution is not well used today. However, Summerfield number is widely used as a indication of load or as a load parameter. Okay, Summerfield number is defined based on radius, which is from there. Okay, and from the also speed. The speed n is expressed as revolutions per second. So the Summerfield number is given in such a set, which is a non-dimensional parameter. Okay, it uses eccentricity, it uses viscosity from the lubricant. Okay, so the dynamic viscosity of the lubricant and revolutions per second divided by the average pressure. Okay, and then R over C, it is a non-dimensional term. So this totally whole thing is non-dimensional. Summerfield number S give us the load capacity. Okay, actually, Summerfield number is the reverse of load capacity because the average pressure here contains the load. But this is a very important parameter. We're going to use this in a class. Thank you.